Yeah, they got it. We tested it already. Okay, cool. Well, thank you for coming to the talk about brain networks and edge analysis. So my name is Josh Faskowitz. I'm a postdoc in the section on functional imaging methods, and I love to talk about brain networks and edges and nodes, and we're gonna go through all of this. So as long as I have a cursor. So I'm going to talk to you today about the brain. And we're going to do a little bit of a brain networks intro. Just a couple days ago, Javier did a great lecture on functional brain networks. So for all you in the room, but also future viewers of this talk series, I definitely encourage you to get a start there, because that will give you a basis in functional brain networks. And then watch this one. So yeah, that'd be a good order. We're going to talk about how we make functional brain networks. We're going to speed through that a little bit, but it's important to go over because the edge analysis that I'm going to talk about builds upon some simple assumptions that goes into making functional networks. And ultimately, we're going to talk about an edgy approach to looking at functional MRI data, or any time series data for that matter. So first of all, here's like my little sales pitch for the brain as a network and as a network system. Right? We know we have all these regions of the brain, and like it's not a monolith. You can slice and dice the brain into various regions, which are all the, little red dots here. And we think that like function is localized for certain things in certain places. Like we all kind of think this, like the brain just can't do everything all at once. There's all these different parts. And it makes really cool pictures too. But studying these parts is a big motivation for using networks. Networks allows you to study all these parts in a principled way. Here's just another beautiful picture, more kind of artistic than anything else, of like how you might have all these little areas of the brain represented by the balls there, and looking at all their interconnections or interrelationships. The brain, too, I would argue, is a network on multiple spatial, temporal, topological scales. But I really want us to focus on spatial scales. So what do I mean by that? At the level of neurons, there's a network. You have, this is what Cajal was talking about and winning a Nobel Prize eventually. So at the level of neurons, at the micro level, we know that certain neurons are connected to certain other neurons in a stereotypical way, especially in model organisms like C. elegans, which we have mapped the whole C. elegans nervous system pretty dang well. This is the best mapped organism, I would say. And yeah. We've also now are mapping the Drosophila. So this is like newer. The C. elegans was mapped, I'm pretty sure in like the 80s, and we've been working on it still, but the newer stuff is kind of the more quote unquote intelligent organisms, but it'll be fun to have these networks. They're a lot bigger, many more neurons connecting, but these are micro, like these are actual neurons touching each other. Then we have meso level, the middle between micro and macro, where I would say meso is like you look at one general area, one little, millimeter size part of the mouse brain, and can look at where it connects to, but using like virology and like injecting some tracers to look at all the connections. And then we have macro level brain networks. So, hopefully we have an understanding that MRI measures the brain at the scale of millimeters, a couple of millimeters at a time. Like that's our resolution. If you're taking a picture, you don't take a picture with MRI of the brain at the level of neurons necessarily, but you can get an understanding of how the brain connects at the level of, I would say an analogy is like the highways. Instead of the individual streets, we could see the big highways of white matter between different areas. Now we can, with layer fMRI, we can get much more micro, I guess. That's more nuanced. But at the macro level, we can measure how these, how these lobes or large areas talk to each other. So what I want to show you here in these few slides is like networks exist. You can take a network's understanding from the micro all the way up to the macro level. And to me, it makes sense to study the brain. Here's another example of macro brain networks. These are the canonical Yao systems. So, we talk about, the control network is this area, this topography of the brain that has this kind of stereotypical map. And maybe all these areas work together for a certain type of cognition or behavior, the default mode network. These are macro. These are obviously, millions of neurons in each of these, supporting each of these networks. Okay, but networks of the brain, why? Why do I like networks so much? Why did I do the whole PhD on this? Why am I doing this in my postdoc? Blah, blah, blah. Well, you can answer some really cool questions, such as like, how important are some parts of the brain? You might measure the centrality of an area. The degree is what we say in network parlance. Oh, can you? Oopsie. Okay, well, you can create models that kind of get at how signal would pass from one area to the next using network models. That's a cool question you can answer with networks. You can ask what parts of the brain are clustered in the same way I just talked about those Yao networks. Those were identified with a clustering algorithm so that you know which part of the cortex topography work in tandem, even if they're not next to each other. And you can also ask, how do we interpret a node in the context of this greater network? So something I always tell people is like, networks allow you, no area of the brain acts in a vacuum. Every area in the brain has its context with every other area of the brain, or every other area it's connected to. Networks allows you to study this. Another cool thing about networks is that you can take general mathematical concepts such as clustering and community detection. So, and you could take these mathematical tools that were developed for a variety of purposes. So this is not a brain network. This is actually a political network of like each one of these circles represents a person and how often they voted for a bill together. And so the strength of the line is like their commonality in bill voting patterns. And you can use clustering algorithms to separate one political party from the other. This is a network of cell phone communication between, I think, teenagers. And you can cluster the network and look at how the activity spreads on the network at different times of the day. That's all to say that like these are mathematical tools that you can apply to generally networks, and then you can also apply it to the brain. So as reviewed in this paper, that we like to cluster the brain to look for areas of cortex that work together. We can also use network understanding to kind of measure complexity or clusteredness. So this specifically is called small worldness, but you can kind of just visually see that this is like a very ordered network, and this is a very disordered network. And you can apply this kind of thinking and measure the orderliness of a transportation network, such as like the subway, or a network describing the interaction of characters in a movie. You can measure this property in these networks and in the brain. I think that's pretty cool. And like I said before, you can measure the supposed communication between areas based on the network properties. So like how many steps might it take to get from one area to the next? That might be, and like, what's the path of communication? And if you think that communication in the brain is efficient, this path to get from I to J would be more efficient, less hops than this path. That's another thing you can do with networks. And finally, this is what I was talking about with the idea that no area exists in a vacuum. It's sometimes called fingerprints in the literature, a connection fingerprint, popularized by Passingham in an amazing review years ago, 2002, I think. To just think about, what's this connectional pattern from this node to the rest of it. Okay, so network analysis allows you to quantify this kind of like very abstract idea of organization with all these different descriptors. So that's why I think networks are cool. We think the brain is not just one monolith. We have all these different parts doing all these different things, interacting, and networks allows you to do that. So just so that we're all on the same page here, all my viewers in the future are all on the same page here. So just some basic network parlance. So we have a brain. This is like a really simple network. Remember that like in actual data, it won't be this simple. It'll be maybe, this is like the Schaefer atlas. You have a lot of nodes here. The choice of nodes is arbitrary, by the way. Get to that later. But you can see how this is like a simpler brain than that. So we call the circle things nodes. Nodes are distinct units of your system. Whether you're in the transportation network, maybe a subway station is a system. It makes sense as a unit of your system. Here, a node on the brain, it just makes sense as you said that this patch of the brain, all the bold signal there is basically a unified thing. That's like a controversial step. We have to do this thing called parcellating the brain to make these nodes, because there really is no ultimate answer. The Human Connectome Project published a parcellation that was close to the ultimate answer, but really the reality is that there's no fundamental parcellation of the brain. I think we're always going to be fighting about how to slice and dice the brain. But once you pick a definition to slice and dice the brain, you call each of those little regions or ROIs a node. And you call the connection between them or the strength or the relationship between them as edge. You can have networks that are unweighted, meaning that this edge is just exists. This edge exists. That's all. There's no number associated with it. Just exists or doesn't exist. So there's no edge between 2 and 7, but there's edge between 2 and 3. But then you could have weighted too, which is maybe like you could kind of intuit that that's maybe a little bit more information. You could have directed networks where maybe there's a relationship between 2 to 3, but not 3 to 2. And I didn't really illustrate here based on the limitations of Google Slides, but you could have maybe bidirectional interactions too, where it's like 2 to 3 and 3 to 2. That would be a directed network. So structural brain networks describe, white matter connectivity between areas. Functional networks describe the similarity between areas. So maybe there's not a structural connection between 1 and 2, but there's a high similarity. We'll get into that in a sec. One thing is that I'm not really gonna show you a lot of networks like this today in the talk. I'm gonna show you a lot of these things. This is called an adjacency matrix. I hope that you'll be familiar with this. I'm gonna break it down for you real fast here, but this is basically a lookup table. This is gonna show you, this is the same information as here. So instead of showing you something like this, because we're gonna deal with networks with many thousands of nodes and many thousands or millions of edges, I want you to learn how to read the adjacency matrix. So like node 1, you would encode that it has a connection with 2 and 7 by putting a little, by putting an entry here at 1, 2, and 1, 7. And you can just continue that all the way throughout the matrix. So hopefully that makes sense, that this matrix is the same information here, but this is a lot more convenient to show and also to load up into your favorite analysis software. So hopefully this makes sense. This is the same information as this, because I'm going to show you a lot of squares today. Okay, good. All right, and so there's a lot of types of edges. I'm just gonna, repetition's the best way to learn here. So again, we have edges that represent connectivity, white matter paths. We have different ways of estimating. You could do the tracer injection, you could do tractography, where you kind of estimate the edge from region B to region A. You have edges of similarity, which is where functional networks fall into, where you take some sort of measurement at one node, a measurement at another node. Either those measurements are a time series and you do a correlation, or maybe it's a different type of measurement where you measure covariance or correlation. And then you could also measure, if there's a certain property here and a certain property here, you can draw an edge between them. That's a little bit more nuanced, but I encourage you to check out this paper, which I'll reference later, to learn about that. So one of the holy grails of network neuroscience generally is to compare structural networks and functional networks. This is a great review in TICS from 2022, but basically they're not the same. But we're trying to figure out how to make them more the same. Is there a communication model that you could estimate from your structure? You had this structure that we assume to be static. Is there a way to read that structural network where you can predict the functional network or the activity that unfolds along the structural network? And that's a big pursuit in the field. Not what I'm going to talk about today, though. But that's just a taste. So this is a slide you can all refer to later if you need to take a screenshot or something. Here's that paper I was going to plug. So published a little review. So this is like a little advertisement for myself and my thesis work. But it really has some good stuff in it. It talks about edges in the brain, and I'm going to talk today mostly about functional edge analysis, but there's some structural edge analysis in here too on structural networks. Okay, very quickly, because I also like to think about data. How are we going to get to functional edges? Well, first you're going to scan a subject, right? We're talking about MRI now. Then you're going to pre-process your data. Then you're going to parcellate. You're going to fit those ROIs onto your brain. And then you're going to measure the time series and then make a functional network, and then it's done. But there's actually a lot of steps in here. Not only are there a lot of steps, there's like a ton of time sinks that could be a whole PhD, just doing surface reconstruction, just doing denoising, just making all these network choices, thresholding your network. It's all tricky business. And one of my pieces of advice here, if I'm being preachy, is to collaborate with people, because no one can know all these different steps to go from scanner to brain network analysis. Along the way, there's so many time sinks. Collaborate with your friends, and then you could do good work and eventually get to publish pretty pictures. Okay, so how do we actually make functional networks? The reason that hopefully you showed up here. So you take a node, take another node, and you measure the time series, right? That looks intuitive. You measure the ups and downs, and you do that for one region, another region, another region, another region, and you can compute all the pairwise time series, and you want to basically compare these. Our comparison metric of choice is usually correlation. Oh, sorry, and it looks like this, let's say. It looks really pretty. Oh, oops. Yeah, so this is actually what real data looks like. This is just from we've taken fMRI data and we've parcellated it. These are our nodes. I don't have any edges yet. These are just the nodes, and these are just an example time series coming out of this. The TR of this data is 1.5, and the GIF is going at 0.75, so it's actually 2 times as fast right now. So in fMRI, just wanted to give you a sense of how fast that's going. But hopefully this gives you an idea of the data we're working with. Okay, and so once we do a pairwise comparison of all the different nodes, you form that matrix like this. So if I had 200 nodes, I have a 200 by 200 similarity matrix where each entry here records how similar one node is to another. This is traditional fMRI analysis. So things you do after this is what Javier was talking about yesterday or 2 days ago. Maybe you do a little connectome predictive modeling, and you look at all the edges here and you look at what relates to behavior. So that's all and good. One thing I want to stress is that when you make this similarity matrix, this FC matrix as we call it, you're comparing the similarity across all time. So all the blue time and all the purple time. You're just getting one value here that tells you the similarity across 10 minutes of how these nodes fluctuate. One of the new hotter things to do, which might give us more information, is to actually do a windowed correlation and to get an idea of dynamics. So maybe we don't want to know how these all are similar across the whole time, but we want to break it down. We want to only measure the similarity in this window, and then in this window, and then in this window, and then this window. Hopefully this looks intuitive. The idea of doing this is that your brain is maybe going through different states. Maybe you're like paying attention in this window. Maybe you've shown your participant a different task in this window. So you want to know the correlation structure here, but you also want to know like what it was before and then how it changed and how it changed. So like this is work pioneered in part by esteemed members of the lab looking at how, so like this would be correlation across the full time series, but if you break it down into what we call a sliding window, you measure correlation across time, you see that there's a lot going on to get to there. So that's like a cool way of looking at the data. Okay, so this will be fundamental for edgy stuff. How do we calculate correlation, the time average correlation? Well, so I'm just going to go through how to calculate Pearson correlation, the traditional correlation we all know and love, and we use, it's produced thousands of papers. Well, you take two z-scored time series. So this blue has been z-scored, this purple's been z-scored, and you just multiply them together, and you get this big number. And you multiply these together. And since it's a negative times a positive, you get a little negative. And you multiply these together. And you do that so on and so forth. So you have these, this blue and this purple multiplied together. And now, if you took the average of all these values, you get Pearson correlation. That is like one way to calculate Pearson correlation. There's like many different ways to calculate Pearson correlation. It all goes to the same thing. Like this is just one way of looking at calculating Pearson correlation. You take two signals, you z-score them, you element-wise multiply them, and then you just take the average of all these reddish values, and that gives you a Pearson correlation. So a few years ago, we said, wait, hold on a second. Why don't we just like get rid of this? What's going on here? What's the red stuff? Well, the red stuff is just the element-wise multiplication of these two nodes. So this is a recording moment to moment of how these are instantaneously in sync. And we thought, wow, this is a new time series, but it's not like a time series of blue and purple. It's a blue-purple time series. We call this the edge time series. So you can see how simple this is. It's just element-wise multiplication. And you can do this for all the different edges in your network. Now, what our first thought when we got these, when we wrote this down on a little piece of scratch paper, is like, let's do some clustering. Let's compare all the edges to all the edges. And we did some clustering, made some pretty pictures, but I'm not here to talk to you about that. I want to talk to you more about the temporal and dynamic properties of these edge time series. So what are edge time series and how do they relate to sliding window correlation? Well, an edge time series, first of all, gives you the recording of instantaneous functional connectivity, right? Like each value here is the multiplication of just a time point with a time point. Whereas time varying functional connectivity, that a sliding window connectivity, you have to, by the mathematical constraints, you need a window that's bigger. And then you take the correlation there and you get your value. You also need to pick that window size, which is like really tricky. And if you're writing a paper, you always have to test different window sizes, and that's like a parameter selection choice. You also have to pick a sliding window amount, so if you slid that much, maybe you like skip some time points here, or you're changing the temporal resolution of your data. And also when you do sliding window correlation, because the Pearson correlation normalizes your data, you're actually normalizing within your window. Whereas the edge time series is not doing any of that. Now, I'm not saying this is necessarily better, it's just different. And we kind of just like these different properties. We didn't have to, edge time series, you just don't have to, you don't have to do any of those choices. You just get instantaneous similarity. Now, one of the questions that pops to mind is like, whoa, okay, if you took a sliding window correlation and just like made it so small, does it converge to edge time series? And the answer is not really. So here, I just made a little simulation. I took out some, these are just two signals. This is the edge time series of those signals. So this is like instantaneously, how similar are they? So you see this like big, see this dip here? That's because this was up big, this was below zero. So like you have zero here. So this is a big positive number, this is a big negative number, so you make a big negative. But then once they're together, they make a big positive. But in the sliding window, you don't see that so much. You actually see it in a different place, this phenomenon right here. And then it kind of moves to more of the edge time series location when you make your sliding window size smaller and smaller. So just goes to show you that it's not identical. They're complementary, of course. They're made from the same data, of course, but they're a little bit different. So just something to chew on if this appeals to you. Any questions about this? Because this is the point of comparison. Yeah, you have a question? Yeah. Yeah. So the question or the comment even was like, when you're doing sliding window correlation, there's a paper by Leonardi that showed that you need to have a certain band pass in your data in order for your sliding window to make sense. And in edge time series, we are totally breaking the rules of bandpass filtering, totally. And I honestly don't know how much that affects the edge time series. Obviously, you're way past the recommendations of that famous paper in NeuroImage. But we're also, there's just no window. So you're normalizing an edge time series across the whole scan. So in some ways you have whole scan information because of the Z-score, but it remains to be seen. Like that's an important, and unfortunately, I'm not an electrical engineer and haven't received enough information.
It just fails just very short windows.
Yeah. So these are the shortest windows possible. So yeah.
Kind of along the same lines, like if you're shortening the window, and like you said, you're just calculating correlation within these windows. Doesn't that mean your normalization factor just drops to 1? So basically, I guess I don't understand the difference because you're still taking all of the values and then you're averaging all of the values within your window. And once your window is to 1, your normalization factor is 1/1 because you put it there.
Yeah.
So then it's edge time series is kind of just a window choice, right? But it's the same formula.
Yeah. Well, but in sliding window, you would normalize, so an edge time series, since you're z-scoring across all your data points, your normalization is across all your data points. Whereas if you keep on shrinking the window and your normalization factor becomes 1 in the sliding window, my intuition tells me that then it's just the value of whatever the time series was going in. So if
So you're saying that in the sliding window case, people normally z-score within the time frame, but it would be identical if they z-score the entire time series first, and then chose the
I think so. That's what my tuition tells me. So if you were to do sliding window on already z-scored data instead of like a % signal change or something like that, then I think they would make sense if they converge. Yeah. Cool. Yeah.
Do you look at the lags?
I have one analysis of lag, but that's a big unexplored area, which I think deserves exploration.
This is
It's ROI wise, yeah. ROI wise. Doing edge operations at the voxel level is prohibitive because it explodes the dimensionality of your data. I think I might get to it in a slide. I'll show you. But yeah, this is at the ROI level. Usually, nothing's stopping you from doing it at the voxel level besides RAM, because basically you take, if you had 10,000 voxels, you would make 10,000 times 10,000 minus 1/2 edges, which is a big number. So not good for RAM. But if you're on BioWolf, the NIH computer, maybe it's possible. But then I don't know. Remains to be seen what that would get you. Yeah, like a seed. Then you'd be much better. That would be only a 10,000. Yeah. So yeah, like yeah, exactly. Yeah. Cool. Okay. Going on here. So just to stress that the Edge time series, one of the reasons that I think it's cool is that this has a direct relationship to time average correlation. All we did is take Pearson correlation, which like there have been thousands of papers on Pearson correlation, functional connectivity studies. We've just taken correlation and looked at its guts. We've unwrapped it. But like if you took the mean, we're just looking at the little parts that make up correlation. You know, by avoiding the window, we're just looking at correlation, just unwrapped, which I think is really nice because it gives us a grounding. So this is just a little to illustrate, like just to illustrate what these edges look like. So if you had an n by n connectivity matrix and you unwrapped all the edges into one long vector, this is what all your edge time series for a data set would look like for one subject. So you have edges and time. And the cool thing about edge time series, but also one of the prohibitive things I just mentioned, is that every single column is a square matrix, is an instantaneous connectivity matrix, so to speak. So right, you could look at the column here and look at that thing, and look at the column here and look at that thing. So edge time series explodes your dimensionality. You've taken data that's nodes by time, and you've made it nodes by time. So you need a big computer. So that's one of the downsides, but also one of the areas of opportunity. And what I mean by that is, okay, one of the initial things we did with these edge time series is we took the edge. So we compared the node by node matrix, the edge by edge matrix. This is averaged across time. I just wanted to demonstrate that by exploding the dimensionality, we showed that you can get higher identifiability. So this is a kind of like brain fingerprinting, not in the sense I talked about before, but like if I had 2 scans, could I identify my second scan as opposed to someone else's second scan? With the edge time series, using the higher dimensionality, you can achieve better identifiability. That's just an aside. So that there's the proof in the pudding. You get higher number, better with the edges than with the nodes. That's just like a simple demonstration of like maybe a benefit of exploiting the dimensionality. Okay, but back to the edge time series. Okay, so we have like these edges and time, and each one of these columns makes a matrix. You have all this data. One way to summarize the data is to actually do something really crude and simple, but maybe kind of useful. You could just take the RMS, the amplitude of the activity at each column. And what this kind of tells you is like the instantaneous similarity amplitude. So we call these high amplitude events. So this is the time series of how much instantaneous connectivity is going on. So you can see like this, all the edges and by time, it doesn't look smooth. It looks kind of bandy. So that prompted us to look at like, oh, there's some points in time where there's like a lot of connectivity happening. So you can kind of see this in this little GIF I made where like, we're going to get to one of these RMS peaks. Whoa, A lot more yellow there. Oh, here comes the yellow. Whoa. A lot more yellow. So that's just this is the same kind of data dimension step, data reduction step that I did here, just in a little GIF. So you could see that like, first of all, this demonstrates, every single time point you get a square matrix. And if you just measure RMS, so really crude, right? Like we're collapsing over a lot of numbers, but you see how something's going on. So we got really hooked on looking at this because we're asking, what's the nature of connectivity dynamics? Smooth or punctuated? Like when we take the Pearson correlation and unwrap it, like what's the nature of this unwrapping? Well, some people could say, like maybe there's these like, I would say that this paper argues for sort of a smooth process unfolding. There's these quasi-periodic patterns, perhaps, that like, there's a symphony of these different patterns, low dimensional patterns happening across 18 seconds. That's one way of looking at it. Eigenconnectivity, you look for the expression of these eigenmodes, and they're not the fastest things happening here. So that's like one way of looking at it. Some work pioneered here at NIH kind of maybe takes a different view. These are called coactivation patterns, CAPS. And I would say that this kind of qualifies as like more of a instantaneous view of connectivity, like much more spiky, kind of like the stuff that we were seeing much later. They published this in 2013, where you have a template, a correlation map, and you look at the similarity to your template spatial across time, and you see these peaks where there's a lot of similarity to this correlation map at this moment, but it's definitely pretty spiky. And finally, like Tagliazuki, another pioneer of this work, said that, hey, I could take the time signals that we get from fMRI and literally just turn them into point process. Oh, no, go away. This thing I want, sorry. Basically make it into a bunch of points. There's a point and then nothing, point, nothing, all because you went over this threshold. So it's almost like a Morse code or something, beep, 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 beep. And showed that this works at the node level. And I would say we can show measuring edge time series and doing the same sort of operation that connectivity could be bursty. It could be this like point process. So really simply, I'm showing you here two edges. So this is our seed ROI. Oops. And this is this is the edge time series from this seed to the blue. And you can kind of measure just the number of spikes. There's 40, sorry. There's 40 spikes here, contiguous times above an arbitrary threshold. And in this low connectivity edge to the yellow, there's not as many spikes. Oops. So what we've shown here is actually really similar to what Tagliagucci was showing, is that just counting, getting rid of all the interesting patterns of ups and downs, the peaks and the valleys, you could just measure this like point process, and it really recapitulates correlation values. So I thought that was interesting. This holds true. I just showed you one seed ROI, but it holds true across the whole brain, just for your edification. This is another way of looking at it. So I took an example edge time series, and I'm just retaining just the edges that exceed a certain threshold. And I'm showing you when you take the mean, like how many times, or sorry, the sum, the count, of how many times each edge. Remember, all these edges fit, if you average them, they fit into this matrix here. And then we measure the similarity of this to this. This is the time average functional connectivity. And you see, actually, you could go up to a threshold of 2 and be very similar. You could basically destroy all the interesting continuous information up to a threshold of 2, which is like right there, and still maintain similarity to FC. So what does this suggest? It suggests that like when there's these big spikes, there possibly is important stuff going on. So what if we just like only looked at the big spikes? Well, we've kind of shown this a few times that if you just look at only, like, let's say there's 1,000 time points here, and we just looked at 5%, the top 5% spikes. The information that we can glean from 5% of the data looks basically like your time average FC, as opposed to the bottom. Like the bottom looks like pretty noisy, which is a pretty interesting outcome. Here's another illustration of that. Just measuring 5% of your data makes a very nice correlation structure that looks like your FC matrix, which is modular like we'd expect. So another thing you can look at is how, okay, you have these spikes and we just like, we just average them all together, but actually we could subcluster the spikes. So maybe like there's like a spike and a B spike and a C spike and a D spike. So if you just apply clustering, you can get different spike patterns. And they kind of look like, the first spike pattern looks like a default mode spike. So this is very similar to like a CAPS analysis, where like you see the default mode out of your edge, using your edges to pick it out, you see like a default mode happen with very few time points in your scan. Or you could see connections with the control network, for example, here. Another way of doing this, so I just described how you could take all your edges and collapse into one global time series, but you can also do this system by system using the canonical Yao systems we all know and love. So if you just took the RMS, the root mean squared of each system at a time, and then average the top 5% of only those subsystems, you get something that looks like this. I know that this totally looks interpretable to non-super network nerds. So like, here's what it looks like on the Cortex, but you can see the signatures again of each of the systems that we all know and love. One of the interesting things through this edge time series work that we noticed is that, so on the topic of just like reducing the supposed information in your data by making the data more simple, like edges are either on or off. We said, well, okay, wait, edges that are just let's take our edge time series, but now we're just going to say anything above 0 is on and anything below 0 is off. So, which is like really a simple distinction. If you take that data, you make something like this. And actually, one of the interesting things is doing this operation divides your network at every single time point into 2 communities, and up. So your edge is above and above, or your edge is below and below. It makes an up and a down bipartition is what we call it. The cool thing you could do, first of all, taking the edge time series and binarizing it and measuring the agreement as opposed to the FC, these have a 0.96 Spearman correlation. Basically the same. Like we've gotten rid of all continuous information here from the edges and just kept ones and zeros, and it makes basically the same data, which is like pretty cool, I think. And another thing you could do is you could take, this simplifies this game of at every time point, you can create a comparison of like what's going on at this moment to a basis set of these canonical Yao systems, of which I'm showing you a couple here. So it's like a basis set of like a visual, like each of these is a bipartition of, you can measure the template similarity across time. Just a cool thing. So basically, what I want you to take away here is that there's a lot of information, I think, in little bits of your data. I'm not the first person to say this, just edges is a different way to discover what the CAPS people were also saying, or Tagliazucchi was also saying, or other people looking at paradigm-free mapping, for example. There's a lot of the low-dimensional structure of fMRI in these brief moments, which I think is cool. It's something to explore. All right, what about motion and other mischievous stuff? Well, good thing I have no more time, so I don't have to, no, I'm just kidding. I will talk about it. So in our initial look into this stuff, we correlated edge time series amplitude with motion. This is the one slide with lag. So we tried to look at, does the edge time series RMS relate to motion? It didn't really look like it, nor did it look like it related to respiratory rate, heart rate, or frame-wise displacement. But the story's not over here. I think that there's a lot more to be done in this space that me or my colleagues haven't done. And actually, one thing that excites me along these lines is this recent paper in Nature Human Behavior, which says that the variance in your scan goes up over time. So this is the idea. So as illustrated right here, and if you do this rapid tide correction, you can get rid of that essentially. But this actually would come out in edge time series. This means you'd see bigger ups and bigger downs. So this is definitely a pernicious, not real thing that could affect edge time series analysis. So I'm excited to see how this could even make our work less noisy. So here is an example of simulated data where there is no motion possible because just simulated. My friend made some correlated oscillators. We're using the Koromoto model and measured the edge time series, and you still see the spikes. So no motion, no physiological artifact possible because this is in silico. So how do you still like what the heck is going on there? Well, there's been some great papers that break this down and have essentially shown that when you have a system that's correlated in general, you can get these spikes. So it's not necessarily so amazing that we see these high amplitude connectivity events. They're actually signatures of your static correlation structure as well. So what I mean by that is like Ladwig and company, they took totally uncorrelated data, they projected it into a space with correlation. So they have nonsensical data, but with a planted correlation structure. And they actually noticed event-like phenomena as well. So it's not that these edge time series are fundamental things that only happen in brains. They happen in correlated systems. It's a mathematical necessity, I would say. But this also is like chance to explore. So this is just something else we showed in a OHBM poster of ours. Like you get just higher amplitude when you simulate data using like a correlation structure with those communities, and you get less high amplitude with almost no structure. And yeah, I'll skip over that for now since we're running out of time, actually. Okay, so one big question is, okay, these are great. Josh, you really been a part of a lot of papers that show these maps across the brain, and like edges are cool and they make really pretty pictures, but like how do they relate to like the brain actually doing anything besides making pretty pictures? Well, first of all, the edges, they do synchronize across movie data. So I just got finished telling you that like they're a mathematical necessity, but they also have some tethering to cognition. I totally believe it because if you look at movie data, you see banding. So like the edge events, the correlation goes up at certain times. We would hope so. It does that also in dynamic connectivity. This work was extended to show that there are times in your movie data at the boundary between movies in the HCP data set, you see these big edge events. And you also see edge events that are related to things happening in the movie. You can separate those out. And the edge events, if you measure the topography of what's happening at those at the boundaries, they all sort of look the same. Everyone is getting like a big visual bold co-fluctuation amplitude. So these are all pretty like everyone is going when you go from one movie to the next movie, you get a stereotyped pattern happening at the edge level. Whereas for the movie events, it's less similar. And for the random events that happen as even less. Okay, that's movies. Oh, I guess more movies. This is work that my friend did where they took the concept of inter-subject functional connectivity analysis, but performed it on edge data so that they could look, if you took the edge time series and related it to when faces appear in a movie, you could actually see the edges that are related to those faces appearing. that's an example of relating it to behavior. And they had some theory about the face network and how these certain nodes are important for face network communication, perhaps. Another work from a colleague of mine showed that the RSS amplitude is not like, maybe there's actually some more information if you don't look at just the biggest amplitude events, but if you looked at the mediums, just the local ups and downs, these MX. The takeaway here is that MX had the highest predictive value when used, like if you just took, so if you looked not at all your data, but just at these points, the oranges, the local maxima, you can average that data and then use the connectome predictive model and predict intelligence of your subjects better than actually if you took all your data. So just different ways of slicing and dicing time. Finally, I think this is a really cool study. It's still on bioRxiv. I hope it gets published soon. So, yeah, cool. Zeng and Rosenberg, they took two different fMRI data sets, both related to surprise. And so they have this little game here in the scanner where I guess this like bag of money or something falls, you try to catch it, and based on some random perturbation put into the game, subject should be surprised. They have this other data set where based on like a bucket being scored in this NCAA game, there'd be surprise. Like if the losing team scored a 3-pointer or something, or had like a big jam put back, there'd be some surprise. You could see that like maybe surprise, like these are behavioral traces of surprise in these different data, and they look pretty brief, intermittent, punctate. So edges might be a good candidate since we know that edges are pretty brief and punctate. Maybe you could relate what's going on here and pick out certain edges in the brain that relate to these phenomena. And what they did is they extended connectome predictive modeling to pick out a cluster of edges that do relate to these time series. And importantly, so an important validation is that they actually trained a surprise network, like this cluster, on one data set, but then they were able to predict surprise in the second data set. So like a totally different fMRI paradigm, totally different data, and it worked. So I think that's like so cool. Importantly, also, if you dig into this paper, they showed that this modeling, if you tried to use a sliding window correlation and then measure and like look at this and play this whole game, sliding window correlation didn't work. So it's an example of like where edges like work for behavior. That's like fantastic. You can also do use their model and look at the traditional node time series. Importantly, this worked. Actually, the effect size is a little bit bigger, but it didn't generalize across the data sets. So in this case, they really showed that edge time series, a model built with edge time series data, worked better than nodes. And some of our own work here, just really quick at the end here, we're trying to look at different features you can read from edge time series. So edge time series are these spiky, time series of instantaneous similarity, and you can now measure what you want. You can actually measure the dynamic variability of the edge time series. You can measure the magnitude within a window. We can go back to adding windows back to the edge time series, and you can maybe get different temporal information. So what I'm showing you here is a traditional sliding window correlation of just like two random signals here, and that's the darkest green. And you can also measure like dynamic variability, so the variability within like a 30-second window, and that information gives you a little bit different of a path here. So here's another example of that. And what we can do is, so this is something that relates to a paper from the lab from a few years ago, where you want your information from the memory task to be similar to this memory task, but you don't want it to be similar with the math task. You want your signature of fMRI connectivity to be maximally similar between same tasks, so memory, and video, and rest. So like this data comes from subjects who had to sit in the scanner for a really long time and do 4 different tasks. And this is that task design matrix. So ideally, you want your data from here to also relate to the data from here, because that's the rest and the rest. So if your data perfectly, uniquely captured each of the 4 tasks, this is what your task structure should look like. And sliding window correlation, traditional sliding window correlation, a lot of people do. You get data that looks like this. But if you read a different feature of edge time series, for example, if you measure the dynamic variability, you get something that looks like this. This is actually not better, but I'm just showing you as an example that there could be different information to glean by opening up and seeing edge time series. Okay, final thoughts, bringing it home. So edge time series are a new view of the original data. So the data you get from your scanner and you pre-process, you can take FC and get a correlation structure. You take this data and also get edge time series. It's all the same data. I would argue there's no new capital I information. You can't, that's actually a tenet of information theory, right? You can't actually can't make new information. There's information here and we could just extract it. And so by putting the data in this form as opposed to this form, you have an opportunity. You have an opportunity to cluster the data, like maybe you have modularity maximization. You have this code that needs a square matrix, or you have this code that needs a rectangle matrix, and you want to run it on edge time series. So basically, you have your data, and you're just able to view it from a different angle using edge time series. And sometimes that allows you to do better than traditional. Or sometimes it doesn't even allow you to do better, but just different. It allows you to see some stuff that's more punctate, that has less autocorrelation. It's just a different way of looking at the data, but it's not new data. It's the data is already there. It's just a different form. So that's what I want you to take away. It's like a new form of connectivity data. And eventually, remember, the mean of this stuff is this stuff, but we're just opening up, we're unwrapping it. And that's it. So I want to thank my lab, my colleagues, all my colleagues from Indiana and around the world for doing all this work. Obviously, my own work is only a minuscule percent of all this stuff. This is all a huge team effort. Yeah, so it's all fun. And I'm glad you stuck around and learned about some edgy stuff. So thank you. And thank you to my future viewers on the NIH website. I acknowledge you and hope you had a good time. So are there any questions?
Can you look at edges of edges and correlations of edges?
Yeah. So yes. So that was, I really glazed over it because, or glossed over it, sorry. Because it wasn't the thrust of the talk, but our first thing we did with edges is made a huge edge by edge matrix, which we called the EFC matrix, the edge functional connectivity, a horrible name. But so instead of having a node by node FC matrix, as we all traditionally love, we made an edge by edge matrix where we took each edge time series and then just did the pairwise comparison between each edge and all other edge. So this makes a massive matrix. And what we did is we did modularity maximization and k-means. And what this gets you are edge communities. So if you take that data, so you have this huge edge by edge matrix and you cluster it, you figure out what edges look similar. And the cool thing is that you can actually map that data back to your nodes. And then you can actually color all your edges by your community label. So now, if I had a 200 by 200, well, I had 200 nodes in my brain. If you did traditional community detection, you would say these 50 nodes are the red community, these 30 nodes are the blue community. But now, when you get edge communities, you look at one node and it has 199 edges. because it has a connection to all the other edges besides all the other nodes besides itself. But each one of those edges has a community affiliation. And what we did some interesting stuff there where we like measured like for certain nodes, are basically all their edges in one edge community, or is there like a homogeneous mix? Maybe it's like evenly spread along 5 communities. That's some other work we did. But yeah, you can do that, but it's the game of clustering is a bit more descriptive, and my own personal interest shifted away because that's more of just like mapping for mapping's sake. Sorry for all the future viewers. It was good work. I really liked it, but it doesn't get us that behavior, for example, not too much. But it is something we did. Yeah, that was our first inclination because we love clustering. Everyone loves clustering, and clustering is like a fast, fun thing to do. Hopefully y'all got that a little bit.
We have a couple of online questions.
Oh, sweet. Should I read them?
Or I can read them to you.
Well, I'll go ahead and read them since I think it'll come through the microphone. So since the edge time series are normalized with z-scores, if the distribution of edge time series values is not normal, often the case with neuroimaging data, would it not end up with some edges inflated? Are you doing element-wise multiplication? Yes. How do we then know which edges are purely from bold data versus bias from the scanner or something else that causes skew in the distribution leading to biased z-scores? Yeah, that's a great question. That z-scoring can't handle, and thus it's a bias that stays within the edge data. So the study from Nature of Human Behavior, it really shows the bias across time related to variance. The bias related to like the time series not being totally normal. I've looked at normalizing with a median instead of a mean. And just I unfortunately I don't have any empirical data to point to, but just in my MATLAB window, it's different, but it doesn't look that different when you have a lot of data points. That's been my own personal experience, but obviously the bias that the question is talking about is real. So it exists, and it's there. In my own work, it just hasn't been so pernicious, I guess. And then the next, so my answer to that question is that we can't account for it. In my own experience, it doesn't affect what I've been doing, but it's real. And there could be creative ways to get around it, but it doesn't really affect my own stuff too much, even though it's real. And not delegitimizing the question's good. Okay, next question. Max Shine and co. previously suggested using multiplication of temporal derivatives. Is focusing on original activation time series better or just different? Definitely just different. Yeah, MTDs are really cool. And if you read that paper in Network Neuroscience, we acknowledge MTDs are a previous kind of edgy way of looking at things that predate edge time series. And I actually am fascinated because that multiplication of temporal derivatives is you calculate it by taking your the difference from time point 1 to time point 2 and time point 2 to time point 3 and so on and so forth. And you take those and you multiply them. So you get something really similar to edge time series. And you can use that to do some edgy analysis. In the original formulation of the work, they smoothed the data, the multiplication, the MTD data, which I wish they wouldn't have done, because then you don't get as fast of stuff happening. But that's just my own opinion to see fast phenomenon like events. But the multiplication of temporal derivatives does give you more of a sense of the variability, I would suppose. which is what I'm getting at in the current work I'm doing. So it's really relevant. But yeah, definitely edge times are not better. They're just different and really highly related. I'm sure if you took the RSS amplitude of MTDs, it'll look similar. So thank you for that question. Any other, or should we all, oh yeah.
Assess similarity versus cluster correlation. Right, for experience states.
So the question, as I understand it, is you're asking, is there any, like you have the RSS and like, for example, I showed the RSS, the systems, and you're asking RSS, could you make RSS similarity and compare that to like average correlation or something?
Clustering correlation.
Clustering
I'm
correlation.
just trying to understand, is there a special feature
Uh-huh.
coded in the RSS? Like those 5 points might be indication of brain state that is very clustered.
Yeah, no, they
And
definitely
edge
are.
time series are big.
Yeah, so at the peaks, at the high amplitude RSS events,
Yeah.
we found that that's really where the canonical systems like look like they're expressed. So like those RSS, like when you take the high RSS events and look at their structure, it looks like it kind of looks like your default mode network signature. Or if it's a different, like the RSS events, I went through it really quickly, but the RSS event, there's different types of events, let's say. There's A, B, C, D. And they kind of look like, one could be like the motor network, like it looks like that. One thing unexplored, which I'd like to explore, is like the timing, like the transition from default mode to controller or something like that. Because really, you know, it's the pattern, it's the dynamics that we've opened up, that we've looked at, like this whole Pandora's box of edges, like the timing of the edge pattern. That's where real juicy stuff lives. Because right, if you just took average measurements from the edge time series, like if you just took the mean, you just get back FC. So you don't want to do that. That's just back to square one. You want to take some interesting variability measurements, multiplication of temporal derivatives, stuff like this, that really measures time. All right, well, thank you for staying 10 minutes longer than expected. And thank you, online viewers, for an hour and 10 minutes of your time. And let's go watch some Olympics.